Hello and welcome. In this video, we're going to be talking about a PLC. What is a PLC? So simply put, PLC is much like a computer. However, it's industrial hardened and it also has some special requirements depending on the environment. And they typically will accept and read inputs much faster than a typical computer because the types of inputs that a PLC receives are things like sensors that are monitoring processes that change fast and therefore require a fast real-time operating system. Um, that is different than your typical personal computer. So with a PLC, we typically have input sections, which are monitored via input cards on modular systems. Some PLCs have some fixed I/O that are directly on the same board and part of the processor. Then we have a microprocessor or CPU. We also have memory, and then we have a output section. Typical inputs for PLCs are going to be things like switches that monitor different process conditions, such as pressure switches, temperature switches, level switches in the form of capacitance or floats. You also have analog inputs that are things like temperature transmitters, level transmitters. You can monitor level via radar or through pressure. Then you have a microprocessor or a CPU that is interpreting those inputs and through logic is determining what to do with the outputs to ensure that the process is running smoothly and as expected. So then you also have a output section, which is similar, where you might have a card, or if it's fixed I/O, you could also have outputs directly on the PLC or as part of the PLC. And that's typically tied to things like lights, motors, valves, heater elements, different things that are actually controlling the process. So why was the PLC invented? So before the PLC was invented, the automation was performed by using a series of electromechanical relays that had built-in timers, counters, or sequencers. Uh, these control panels could contain hundreds of different electromechanical relays. They were all mechanical devices, so it's very easy for these devices to break down over time. They only had a certain amount of uses, and it was very difficult to troubleshoot these types of systems because of how complex they were with wiring. And anytime you made a change, it required a huge undertaking. You'd have to rewire the system and retest the system. So PLC replaced that by putting a lot of the functionality of the timers, the counters, the sequencers, and the controllers directly into computer functions. And before the PLC was invented, reliability was pretty low and the maintenance costs were very high because any change that you made required rewiring the system. And these were very complex control panels. So it was highly difficult to modify or upgrade the existing control panels. So in 1968, the General Motors Company specified a device that would become what we know today as the programmable logic controller. The invention of the PLC is attributed to Dick Morley. So on the outside, it can be easy to see a PLC is just simply a black box with wires that are bringing signals in, and it has a series of other wires that are sending signals out, and everything that's happening in between is considered magic. But the reality is, a PLC is actually a computer. Somebody had to program the PLC to tell it what to do. The PLC knows what to do based on the program. And this program was developed, compiled, and downloaded and committed into the memory of the PLC. So without a set of instructions and algorithms and programs and code telling the PLC what to do and how to interpret the inputs, it's really nothing more than a box full of electronic components. So every PLC is going to have at least one microprocessor. Many of them have multiple microprocessors, and this processor is typically called the CPU or the central processing unit, and it organizes and monitors the control throughout the whole user program. Typical workflow of the PLC is the processor will read input signals, and then it follows the instructions that a programmer has written that were downloaded and stored into the PLC's memory. And the result of the solves program is that the PLC will write information to outputs or field controlled devices, which either turns them on or off or sets them to specific positions. And the result of the logic that is written by the programmer is that the PLC will write information to outputs based on the inputs and the algorithms associated with them. And it will control field devices, either turning them on or off, setting them to certain positions, placing them in specific modes, or other various output commands that can be generated from the PLC. So some common PLC inputs are going to be push buttons, selector switches, limit switches, level switches, prox sensors, photo switches, relay contacts, motor starter contacts, and then you also have analog devices like level transmitters, pressure transmitters, temperature transmitters, motion sensors, and various other types of contacts. Some common PLC outputs are going to be things like motors, lights, fans, pumps, relays, alarms and bells, or solenoids. But there's also analog outputs like control valves that are setting things to a specific position. There are certain types of heaters that take pulse width modulation signals that will allow you to control a precise temperature. So a lot of different types of outputs that are commonly connected to a PLC. And this is just a summary of some common industrial hardware that represents on or off inputs or outputs. Often PLC programming classes will have you do binary conversions. It's becoming less necessary as it used to be, just because a lot of systems will have implicit binary conversion directly built into their platform. But it's always good to know the why behind certain things. So originally when PLC cards first came out, the input cards were organized into a 16-bit word, and then each IO point is represented by a bit within that word. So you can see if we look at this card, it translates to the numbers 0 to 15, and that can directly translate to a binary number that will represent the on or off state of each one of these bits. So just to review the typical workflow of a PLC, usually on the left-hand side, you have inputs that are coming in that are sensing the on or off state of a field device. Then you have a CPU that contains memory and is powered by a power supply. And that is the device that the programmer will write program, download, and compile to. And then you have produced outputs, typically on the right-hand side. And this is where the program has been solved and executed, and then outputs are written to various field devices to control and maintain a process. With Rockwell PLCs, each card is referred to as a slot in the backplane. So when you address cards, it's important to know the slot number because that's how you will address the individual bits of that card. That's how you'll access and monitor the inputs of input cards. That's how you'll write and access the output addresses of output cards. So it's important to know the slot layout. And this diagram shows you that typically, especially with older systems, the SLC 500 series PLCs, the processor is always in the 0 slot. As you get into newer PLCs, the slot can change. It doesn't always have to be the 0 slot, but in the SLC 500 series, it does. And then you have additional slots depending on the size of the backplane. And in this example here, we're showing a 7-slot backplane, and we start our slot number at 0. So the CPU, like I said, is always slot 0. Then we have slot 1, which is showing a 120-volt input card. Slot 2, we have a 120-volt output card. Slot 3, we have a relay out card. Slot 4, we also have a relay out card. And then slot 5 and 6 are empty.